Hello, class. Continuing section 5.5. You can see this one's quite a long one. The last of the theorems we're going to introduce is called the intermediate value theorem. Out of the three theorems that we talked about in this section, this one you'll probably use the least unless the equation gets really complicated. And in this class, we don't give you super complicated equations. And so here's the definition. And this theorem is kind of near and dear to my heart. When I was getting my advanced degree in math, my qualification exam, I had to prove this theorem. It's much easier to use than it is to prove. But the theory is that since polynomial graphs are smooth and continuous, there's no jumps, there's no way to do any kind of weird looking things on the graph. If you pick two values for x and you plug them into the equation and out comes a positive value for y, and then another one would be a negative value for y, in between those two x values, there has to be at least one real zero. So the best way to demonstrate this is with a graph. So say like, I don't even give you an equation. And say like I say that you plug in f of 3 and you get -5. So how do we graph that? So this would be 1, 2, 3. 1, 2, 3, 4, 5. So that would be f of 3 -5 is right here. And then say like I plug in a negative value for x, and say f of -1, and say like that equals 4. So -1, 4 would be right here. Now, if you think about it, how do I connect these two dots, right? How do I connect these 2 points? Well, the only way to do that is that you have to cross the x-axis. Where? It has to be between these two. You're not, so it goes nice and smooth. So you would have to connect between those two. Now, the thing you don't know is it could connect this way, right? So that's what we mean by at least one, is that between 2 points, if you plug the x values in and the sign changes for y, the only way to connect those two dots is across the x-axis at least once. Now, the one thing that you wouldn't know, for example, is that say like you have 1 point up here, say like that was 2, 3. And say like you had a point over here that was -2, 1. Now, because the sign of the y value has not changed, you don't know anything about how this graph works. So it could go straight like that, or what else could it do? It could do this, right? And so you don't know anything about the zeros if the sign doesn't change. So there's really 2 things to do. If the sign changes, you know there's at least 1 0, and then you could start plugging in numbers using the rational zero theorem, et cetera, to try to find it. If the sign doesn't change, it tells you nothing. And so let's walk through just a couple of these examples. First one, let's take this equation. And using the intermediate value theorem, can you decide if there is a 0 between x equals -4 and x equals -1? So all you do is plug these in and hope for a sign change. So if we plug this in of -4, you get -4 cubed plus minus 4 squared minus 8 times minus 4. Whew, I should have picked a little different number. So this should be minus 64. And this is plus 16. And all right, and that would be plus 32. And that looks like that would be minus 16. And so x equals minus 1. Plug that in. That would be a little bit easier. Minus 1 cubed plus minus 1 squared minus 8 times minus 1. And so it'd be minus 1 plus 8. And so you see you have a sign change. So what this tells you is that there's at least one real zero, could be more, between minus 16, oh no, sorry, x equals minus 4 and x equals minus 1. So if you think about, there's the eraser. What does that look like if we did that, right? So if this is minus 4, minus 3, minus 2, minus 1. So in between here, we know that there is a 0 and it's going to cross the x-axis in between those. So what would that graph look like? Well, I have it taken out of the book. And so this is what the solution graph will look like. And you could see that we have a 0 right there. It looks like it ends up being between minus 4 and minus 3. But what we checked was from x equals minus 4 to x equals minus 1, we do have 1, 0. So let's do one more example. And so say like we take this same equation and see if we have, what do we have between, probably should have put it on pause here while I erased all this, but it's kind of too late now. So a little delay here, that's okay. So let's say what happens between x equals 1 and x equals 3. So plug these values in again. F of 1 equals 1 cubed plus 1 squared minus 8 times 1. And you would see that would give you minus 6. And then f of 3 would give you 3 cubed plus 3 squared minus 8 times 3. And that one would give you 27 plus 9 minus 24. And that would give you 12. So again, we'd have a 0 between x equals 1 and x equals 3. And again, to show you what that would look like on the graph, this is what that graph looks like. And you can see we have one right there between 2 and 3 with regards to that. And so what happens if you get an answer like this? Let's say we do this. Last of the examples. So like we do x equals minus 2 to say x equals 3. And let's see what we get. So x equals minus 2 would be minus 2 cubed plus minus 2 squared minus 8 times minus 2. So that would be minus 8 plus 4 plus 16. And that looks like that would be 12. So then we plug 3 in. 3 is 3 cubed plus 3 squared minus 8 times 3. And that's 27 plus 9 minus 24. And that also equals y equals 12. So this means you have no idea, i.e. it could be zeros between there or it could not. And because there's no sign change, you can't make any conclusion. And so if you look at the graph one last time, you could see we have actually 2 zeros between there, right? It goes down through the origin and then back up between 2 and 3. But again, you just don't know. So basically the process and the theory is that if there is a sign change, you know there's at least 1 0, and you could start plugging values in between there, try to find it. Or if the sign doesn't change, you know nothing, and you want to try again with regard to that, if you're using that to actually solve the problem. So that ends the recorded lectures for the intermediate value theorem. There's going to be one more lecture in this section, and we're going to walk through a problem and everything that we've actually talked about from section 5.1 through 5.5.